I'm going to talk mostly about intermediate depth earthquakes. This is a classic map showing intermediate in the green and the blue and deep focus earthquakes. And as you know, most of these, in fact, we once thought all of these earthquakes occur at subduction zones like Tonga, the New Hebrides, Marianas, Japan, South America, and so forth. I'm going to start with that idea and go back 50 years ago. Isaacs, Oliver, and Sykes in '68 showed that intermediate and deep focus earthquakes occur within downgoing slabs of lithosphere. So these are 4 cartoons that Brian Isaacs and I put together years ago, showing a slab of lithosphere plunging under another slab. The shallow earthquakes show thrust faulting consistently. And these are 4 cartoons illustrating different situations. In all cases, the open circles indicate down dip compression. That is to say that within the slab, the orientation of compressive strain is parallel. Compressive stress, presumably as well. Compressive strain is down the dip of the slab. Always for deep focus earthquakes, or virtually always for deep focus earthquakes. When there are no deep focus earthquakes, however, the orientation of the strain is down dip extension. The slab is being pulled down, presumably because gravity is acting on the dense material of the slab. Sometimes you have a slab that penetrates to great depth and it's down dip compression all the way along. In many regions, there's a gap in the seismicity, no earthquakes in the lower part of the intermediate depth range, and in this case, consistently down dip extension in the upper part. We imagine that what happens is the bottom part is hitting resistance and hence is under down dip compression, but the upper part is still experiencing the gravitational pull of the dense material and it's being stretched. And then there's an alternative where there's a gap where the slab is broken off and a piece has fallen into the deeper part of the asthenosphere. In a summary of data, sorry, this is flipped to be opposite, but always down dip compression for the deepest earthquakes in all places, with an exception or two that I will not talk about. The down dip compression in many places, such as under Japan, Honshu, Tonga, Marianas, is continuous all the way to the surface. In some places, like under South America, under northern Chile, or under Peru, there's a gap, and we think the slab is detached and has sunk. Under the New Hebrides, that certainly has taken place because of this flat zone down here. But then when you move to places where there are no deep earthquakes, usually, not always, but usually it's down dip extension. So this was the picture that we had 50 years ago, roughly. And the old idea, intermediate and deep focus earthquakes occur within downgoing slabs of lithosphere. Isaacs, Oliver, and Sykes had shown this. And of course, because temperatures are low in this region, the cold slab has sunk rapidly into the asthenosphere. And then we took this and said, conversely, the occurrence of intermediate and deep focus earthquakes implies the presence of a downgoing slab of lithosphere. That's what we thought then. It didn't take long to change our minds. I'm going to skip this slide and move on to the next one. I'm told that only some of you will understand these diagrams. If you understand them, I needn't explain them. If you don't understand them, the fact I want you to take away is they all look pretty much alike. And trust me, what they show is you have roughly east-west extension and thinning in the vertical, thinning of the layer in which the earthquakes occur. Now, roughly, what would it be, 35 years ago, we found 2 earthquakes that were quite a bit deeper than the others. Most were at shallow depths. This is longitude going 78 to 94. Most of these earthquakes were shallower than 10 kilometers, but we had found two at that time, there are now many more, that were much deeper, down at 85 or 90 kilometers. But with the same style of deformation as at shallow depths. These are not within downgoing slabs of lithosphere, but we're quite sure they're in the mantle. Since that time, many more have been found. This is a fairly recent one under Wyoming. This is a map of Wyoming, but first look here. This is a map, Western United States. Yellowstone would lie right up here. The earthquake is at this point. This is a map of seismic wave speeds at 75 kilometers depth. The blue means high speed, presumably cold. The red means low speed, presumably hot. The earthquake occurs at the edge of the blue area. So this red line is a cross-section, profile through. The earthquake occurred right here at the edge of the blue and near the red. That may not be important. The point is it's in the blue where it's cold, and it's 75 kilometers. Just some seismograms. I'm a seismologist by training. It's in my blood. I have to show some seismograms. So the P wave is here, the first arrival, and then there's the P wave that goes up to the surface and reflects off the surface and comes back down, obviously later than the P wave. We call that little p, big P. There's also an S wave that does the same. It's even later, but we don't have to worry about that here. The P and the little p, big P. That allows the depth to be determined quite precisely. What in fact Craig and Hayburn did was they fit these seismograms, the observed seismograms recorded by seismographs, to synthetic seismograms, and then they examined the misfit over many, many of these, not just 4. I'm showing you 4 of these here, but they had tens of seismograms. And they show a misfit here, a misfit calculated in some dimensionless units on this scale over here, and is a function of depth. And again, the depth is about 75 kilometers. Well below the crust goes to maybe 40 kilometers. So this earthquake is in the mantle. And one more, in northern Australia, an earthquake up in here. The depth, 61 plus or minus 4 kilometers. The Moho is down around 35 or 40 kilometers. So another earthquake in the mantle. So we have earthquakes occurring within the mantle in many, many places, including many at intermediate depths. By definition, intermediate depths are 70 to 300 kilometers. And in several regions, southern Tibet, Wyoming, northern Australia, plus other places where these have been found. But these earthquakes do not occur in dipping zones. They don't occur in sinking slabs of lithosphere. They simply are in the mantle. They're telling us the mantle is cold enough for there to be earthquakes in these regions. Now, if we go back to this synthesis that Isaacs and I put together long ago, we considered many, many regions. This was a global summary of what we knew at the time. For instance, the Aleutians, Kamchatka, Japan, and so forth. All of these areas, except 2, are classic subduction zones. The Andes under South America, Central America, the Caribbean. There are 2, however, that are exceptions. In the Mediterranean area, of course, you have the Calabrian and the Aegean area, but you also have earthquakes under the Carpathians. And in the Hindu Kush area, Pamir Hindu Kush area, again, you have earthquakes that do not seem to be in downgoing slabs of lithosphere. I should say this is controversial. Others would disagree with me, but these 2 regions are different in the sense that the evidence of subduction is far less convincing than elsewhere. So I'm going to show data from both of these regions separately. These are studies by others, not by me. This is first just a map of the Carpathians. Over in here, you recognize the Alps, the Adriatic Sea, the Black Sea, the Carpathians. The red is showing fairly young calc-alkaline volcanic rock, the kind of rock you associate with subduction. But all of the intermediate depth earthquakes are in a cluster over here in the corner of the Carpathians on this side. If you look at a blow-up of the region, again, this is the corner in the Carpathians. These are these same diagrams as before. The only thing that you have to know is these, almost every one of these, consistently show vertical extension. The region is being stretched vertically in a zone. The seismicity goes in a vertical zone, goes down to about 200 kilometers depth. Now, if one looks at the tomography, the seismic wave structure of the region, First, let's look at this profile 4 prime coming across here through the seismic zone. The earthquakes are these little green dots in here. They go down only to 200 kilometers or so. The blue is showing high-speed material, presumably cold material, sinking under that region, flanked by lower-speed material, as shown by the red. If you look at the longer profile across all the way from the eastern end of the Alps in Austria across, again, the intermediate depth earthquakes are in here, this blue zone coming down to 400 kilometers, flanked by lower speed regions. If we look along this profile coming along the Carpathians in here, again, the earthquakes are just at the eastern end. Most of the Carpathians are not underlain by high-speed material. They're underlain by low-speed material. So you wouldn't be putting a slab of lithosphere underneath that. This is the only place where you have these intermediate depth earthquakes and this high-speed material. And then 2 more profiles going across in here. Again, it's all low-speed material underneath the Carpathians. So I'm arguing, as you'll see, Lorenzi and Hausmann, that this is a blob of lithosphere that's sinking. It's not a slab of lithosphere. So Piroshka Lorenzini and Greg Hausmann, they examined this first. I'll show you a bit more. But this is a simple calculation made where it's a Rayleigh-Taylor instability, where they have a slightly more dense material at the top, overlain in this case by an inviscid fluid in black. This sinks as a blob into the less viscous material. The maximum stretching is where the red is. That's the highest strain rate. The bottom, it's not being stressed very much because gravity acting on that doesn't have a long fetch on what it's pulling. So you're stretching the most up in here. And what they did, Lorenzi and Hausmann, is to take the seismic moments of the earthquakes. The seismic moments, you ordinarily think of magnitudes of earthquakes as the scaling of the size, but the physical quantity is seismic moment. If you have the seismic moment is effectively the strain associated with the earthquake per unit volume surrounding the earthquake. So you can sum the seismic moments and you can get a strain field. You can divide by time, you get a strain rate field. And what they've done is that these boxes here are showing you in different depth ranges the strain rates that are calculated from the seismicity. It's a logarithmic scale, 10 to the minus 13 per second down to 10 to the minus 18 per second. So 10 to the minus 14 per second, as you have in this box up in here, corresponds to 35% per million years. If you multiply that by the thickness of the layer, 50 kilometers, that's 18 millimeters per year that the material at 100 kilometers moves downward relative to the material at 50 kilometers. And I point out 18 millimeters a year is very fast for Europe. Only within the Aegean do you have rates that are that high. If you include the rest in here, the rest of the seismic moments and the strain rate, you get to 25 millimeters a year that the piece at 200 kilometers is sinking relative to the crust above at around 50 kilometers. This is very fast. And their argument is this is a blob of sinking lithosphere. And this is the argument I'm going to pursue for the Hindu Kush as well. So if we go to the Hindu Kush, this is northern Pakistan, the Himalaya coming up through here. The Hindu Kush come across through there. The Pamir in this region, Tajik, the Tarim Basin over here, and the Tian Shan to the north. The blue dots show shallow earthquakes. The most active area is at the northern edge of the Pamir, up in here. And the intermediate depth earthquakes, you find them under the Pamir coming down into the Hindu Kush over in here. The deepest are in the Hindu Kush. But first I want to talk about the Pamir because this region is more complicated than most, and I want to distinguish the Pamir from the Hindu Kush. So this is results, beautiful work, Felix Schneider and his colleagues, German colleagues, and colleagues in Asia from Tajikistan and from Kyrgyzstan, where they had seismograph stations throughout this whole region. First, to digest this picture, look at this lower cross-section through here. North on the right, south on the left. The blue is into the mantle, presumably mantle lithosphere. The tan is crust, and they're showing underthrust crust down to southward beneath the Pamir. These plots, these color plots, are receiver functions. The colors are showing the strength mapped into depth of the S wave that is formed by the conversion of the P wave hitting some interface. So a P wave comes up from depth, from a distant earthquake, hits an interface. Most of the P wave continues, but a little bit is converted to an S wave, where the S wave is strong. It comes later than the P wave, and from the time delay, you get a depth. So this bright red here is showing you probably the MOHO, the crust mantle boundary beneath the Pamir. Red means you've gone from high speed to lower speed, and what I really mean is the impedance contrast is such that that both P and S are higher speed on the lower side than they are on the upper side. Now this is for the direct receiver function. The P wave comes in, it converts to an S wave in the plane of the ray itself. The S wave is polarized in the direction of the P wave, of the arriving phase, but they also have transverse receiver functions. Ordinarily, a P wave should not make an S wave that is transverse to the direction the P wave is coming. But if you have a dipping interface and the P wave comes in at an oblique angle, it will make an S wave that is oriented transversely. So these are the transverse components. The blue are showing converted phases where you go from a low speed to a high speed. You don't see that in the Earth very often. That's a rare configuration, but it would be the configuration if you underthrust crust into the mantle. So the thought is that this blue is showing you the top of underthrust crust, this underthrust crust down in here. It's showing you the top of that going from low to high speed. They can also migrate these. They can project these, take into account the dip. So this takes into account a possible interface dipping 22 degrees, and you can see some enhancement of the signal at shallow depths in this 20 degree dipping region. And then corrections for 50-degree dips and even 65. And you see slight enhancements at the deeper depths because of this. All of this together is arguing for underthrust crust beneath the Pamir. This would be subduction as we know it. This is not what's going under the Hindu Kush, however, I don't think. So go back to this map. The Pamir is up here. These earthquakes the profile I was just showing you is through the Pamir in this area. The red arrows are showing you GPS velocities. India moves towards Eurasia at this longitude at about 30 millimeters per year. Half of that convergence is absorbed along the northern edge of the Pamir, way up here, not in the Himalaya. The Himalaya come up and continue around. There's not that much convergence absorbed in the Himalaya in here. In fact, when you get to the Hindu Kush in this area, where the earthquakes are deeper, half of the convergence is on the northwest side and half is on the southeast side. In essence, you're straining this whole region compressively, a northwest-southeast orientation of strain. Now, another very nice study by John and Kanamori a couple of years ago summed the seismic moments of the earthquakes in the Hindu Kush. This is a map of the Hindu Kush region. They studied 4 earthquakes in detail. This one is definitely mislocated. They plotted it using the published location, but they found it certainly lay down in this region. And they found that these earthquakes, they studied the last 4, these are very large, magnitude 7.5. These are the largest intermediate depth earthquakes we know. This is not common to have such large earthquakes at intermediate depths. And they recur almost periodically. And if you take the seismic moments and you take the dimensions of the fault that ruptures based on the rupture area they find, you calculate vertical extension at about 100 millimeters a year. That's very fast, no question about it. Recurring very large earthquakes at this rate. That means in 3 million years, you'd stretch out a zone 300 kilometers long. That's almost the whole depth range. Their interpretation is that you've underthrust India beneath, the Hindu Kush would be in here, and now you're breaking this through. A slightly more recent study concluded much the same. This is work by Sophia Katharina Kufner and her colleagues in Germany. They looked, I'm going to show only this part. So this is the Pamir region of intermediate depth earthquakes. This is the Hindu Kush. These are separate. This is all I want to talk about in here. Again, these diagrams, if you know these, the back hemisphere, these are showing vertical extension within the shallower depth range in here and the greater depth range of the Hindu Kush. This is a longitudinal profile going from the western end to the eastern end of this zone. Very high rates by summing the seismic moments, very high strain rates. This is the same, generally the same as what John and Kanamori found. These are plots where the axis is different in each case, different time periods, different values for the coefficient of the shear modulus, and different assumptions for the thickness of the seismic zone that's involved. But all of these are in this range of strain rates, which if we convert to geologic strain rates, are getting in the range of 30 or 40% per million years, unless you're in this area where you're up at around 200% per million years, a huge rate. And in the summary that they gave, this is now Kufner and her colleagues, the average rate they get, 42% per million years over this depth range, from 180 to 265 kilometers, 85 kilometers thick. That would be 36 millimeters per year. Again, a very high rate. In this narrow zone, it would be even higher, much higher by, well, 170 millimeters a year. The strain rate at shallower depths is much lower, lower by a factor of 4 or 5. Yeah, that's what I want. So this is the plot from John and Kanamori. This is a little confusing for you. North is on the left, south on the right, India under thrusting, a big fault rupturing through. This is a plot meant to show time where south is on the left and north is on the right. So this is flipped for you. And this is meant to show a progression in time where first you start to thin the lithosphere over here, you rupture through, and eventually you pinch off. The title of their paper includes the words slab break off. They think a slab of lithosphere has been under thrust from the south and is plunging beneath there. But I would like to point out that the GPS shows the convergence is absorbed equally on the northwest and southeast sides. And the evidence for subduction of the Indian plate in this area simply does not exist. It goes back to what we used to think, that intermediate depth earthquakes occurred in subducting plates. In fact, I would like to suggest a simpler interpretation is that a blob of lithosphere is sinking and it's stretching in its vertical orientation. So, go back to the old idea, intermediate and deep focus earthquakes, they occur within mantle lithosphere, but not necessarily subducting slabs. And of course, because the temperatures are low, conversely, the occurrence of intermediate and deep focus earthquakes implies the presence of cold mantle lithosphere, but not necessarily downgoing slabs of lithosphere. These can be blobs that are sinking and stretching. So, seismic evidence from the Carpathians, Lorenzi and Hausmann, and this was the point they were making, this was the conclusion they were drawing for that area, and the Hindu Kush. This is not the conclusion that Kufner and her colleagues or John and Kanamori were making, but their data, I think, shows that you have sinking and stretching of blobs of mantle lithosphere, for lack of a better word, we call it deblobbing, and hence the removal of mantle lithosphere, but this is not delamination as Peter Bird defined the term back 40 years ago. Thank you.